about 2 lectures, so lecture and a half. We talked about mathematical preliminaries, and then we talked about strain and compatibility. And last time we started talking about stress and equilibrium, and today we'll be done with that, which means the next time when we have lecture, we will start applying all of this sort of framework to solving problems, okay? But in fact, I will already solve a problem today just to demonstrate the use of equilibrium in a very practical problem. It's a nice little problem. And this problem we can handle with equilibrium equation alone. So remember, equilibrium says that divergence of stress plus some volumetric force. So components of the stress, it has Newton per meter squared, gradient Newton per meter cube. This is force per unit volume, so dimensions match. And that's equal to rho u double dot, the acceleration times density. So this is our equilibrium equation. And now this equilibrium equation, we have derived it through an indicative procedure, not completely, but our derivation indicates eventually that this is the form that we should be receiving. And this form is valid for any coordinate system, right? Our derivation was based on a Cartesian coordinate system, but this is always valid. So this is something I'd like you to remember and learn. Now, of course, eventually when you like to find the components of f or u double dot or acceleration with respect to any coordinate system, it's very easy. For instance, spherical f r, f theta, f phi, whatever. So that's easy, but the divergence is something that looks a little bit ugly. So that's not something you need to memorize at all, but let me solve one problem where I make use of this equation, and eventually I will express the left-hand side in a cylindrical coordinate system. It really doesn't matter what explicitly it looks like, but we need to be able to interpret the individual components of the stress, its dependence on various coordinates, like we discussed last time, for instance, in a spherical coordinate system for a thick-walled sphere. With the internal pressure, we discuss which components are zero, which components depend on what, etc. Right? So those interpretations we need to make. But once we have the form for divergence, then with that interpretation, we can proceed with a solution. Okay? So now the message I'd like to give with this particular example is, well, actually there are two. The first one is not a message, it's just a demonstration of equilibrium. But the second one is that equilibrium alone, this equation alone, can sometimes help you solve problems to a large extent. Okay? So let's demonstrate that. So sometimes equilibrium alone can help us find stresses, right? Because stresses, components of the stress appear in the equilibrium equation on the left-hand side. So we might eventually be able to directly integrate, this is like a differential equation, we might eventually be able to directly integrate that and obtain the components of the stress. So in this particular example, what we have, it's actually something that you have for sure seen. Let me try to draw it. Does it look like anything? Maybe. For instance, if you have a boat, not many people do, but you can tie your boat. This could be on the shore, right? Your boat could be here, and you could tie it with a spring. So this is called mooring, okay? And you know that the boats are eventually heavy things. They can exert really high forces. That force is that force because this rope is holding this thing. But what people do is you just wind this rope around the steel thing a few times, make a small knot. The purpose of this small knot or whatever is to initiate some small tension in that region. And eventually, it turns out that although you can easily put this knot here, just after a few turns, this rope can carry a very, very high tension. Okay, so we're going to analyze this simple problem. Okay, so this is our rope, and this is the mooring for a boat. Okay, okay. So let me sort of idealize this problem. Of course, we need to idealize. So this is going to be sort of the direction of positive angle for me. So I'm going to look at this problem from the top. And so for all practical purposes, what I will see is just a cylinder. Okay, looking from the top, I'm going to see a cylinder. And on the cylinder, there is a rope. Okay. Okay, so if you like, I'm analyzing just a portion of this problem. Let's say I'm looking at this portion of the spring, and I'm not interested in many turns of the rope around this thing, but I'm just considering a situation where there's some tension on the rope on one side. Of course, in practice, with respect to this picture, this thing turns around the steel support several times, but I'm just starting from one end. And it contacts the support, this thing, at a certain angle. And I'm just looking at a portion that contacts that support through an angle delta theta. And the tension here is T1, and there it's T2. Okay? And I'm going to assume that T2 is greater than T1. That makes sort of sense because the tension here is small, and as I rotate around and around, I expect it to grow. So from in the positive theta direction, this is the positive theta direction, I expect the tension to grow. And of course, the tension is, in a sense, growing because this thing is not frictionless. There is some friction here. Okay? So this contact interface between the rope and the cylinder, it's with a friction constant mu, let's say. Okay. Okay. Now I can draw one more diagram, if you like. I'm going to continue on that diagram over here. And I'm going to draw the free body diagram of the rope itself. So we have the rope. That's T1, T2. Right. So to complete the free body diagram, so what I can imagine is that there are two forces pulling on this rope. There is supposed to be a friction force here, but of course, to balance the upwards force, there needs to be some force that is applied perpendicularly to the rope as well. Okay? So in other words, there needs to be two types of forces exerted on the free body diagram of the rope. One is a normal force. So in essence, what I'm doing is I am distributing or decomposing the components of the force into a normal and a tangential component with respect to the coordinate system. So this direction with respect to my cylindrical coordinate system, it's the r direction. And now there will be a theta direction as well. Okay. This will be in the theta direction, eventually the friction force. Okay. Now the rope we can idealize, or we can think of it as contacting the cylinder here on a line. So this force is going to be force per unit length. So if I integrate the red normal force along the length, I will obtain force in units of Newton. So let's call this W. Okay, W is Newton per meter, force per unit length. Okay, therefore the friction force is also going to be a force per unit length in this case. And so let's call that tau, and that's equal to mu times W, also newtons per meter. Okay, so that is our setup. Now, the rope itself has a cross-sectional area. Okay. Let's call that A. Okay, I'm going to make use of that cross-sectional area. All right, so we have the tension on the spring on the rope. We have a distributed force per unit length in the radial direction and a force per unit length in the tangential direction. That's the positive direction for friction. That's what I assume. So it's in a sense the minus theta direction. Notice because the plus theta direction is counterclockwise, right? So this is minus theta direction. The magnitude is tau, which is friction coefficient, times the radial component of the force, which is force per unit length. Okay, so that's the setup, and that's what I would like to now analyze. Now, I am in the cylindrical coordinate system, and really the portion that I'm interested in is this portion where there is contact of the rope with the cylinder. Okay? So now I'd like to define a stress in the cylindrical coordinate system associated with this portion that I'm going to try to analyze. So I've extended the rope just to make things a little bit clear. Cylindrical coordinate system is our system for analysis, naturally induced by the simplified geometry. So now I have a force. I'd like to define a normal stress on the rope. But that normal stress is the eventually normal stress on the cross-section. The cross-section is the theta direction. So on the plane with normal theta, in the direction theta is our normal stress. So it's sigma theta theta, right? But sigma theta theta, in reality, perhaps it is not a constant over the cross-section. Perhaps it varies a little bit. But I'm not quite interested in the exact variation. What I'm going to do is I'm going to define sigma theta theta as tension divided by the area. So in a sense, this is some average stress. It will be sufficient for our analysis purposes. This is something that we will do once in a while, right? Okay, so that's sigma theta, and notice that sigma theta theta is a function of theta alone. So there is no radial direction. The rope has a certain thickness. I already averaged the force over the cross-sectional area, so I don't worry about variations in that direction nor in that direction. So the only variation, therefore, will be along that direction. The tension changes from this point to that point, and therefore the average stress changes from that point to that point, and that direction is the theta direction. So sigma theta theta depends only on theta. Okay. All right, so now we will go ahead and write equilibrium. This is a 2D problem because the axial direction in this case would be the alta plane direction. I'm not interested in any sort of variation. There is no such variation in the third direction. So I'm going to, with this setup, going to completely ignore that third direction. So it's an intrinsically 2D problem. So eventually, as I expressed at the very beginning of the course when we were talking about divergences, etc. In your online reference, for instance, our reference book, you can find expressions for divergence of stress in, for instance, a cylindrical coordinate system. So when you look at that expression, because it's 2D, first you have to omit Z components. Okay? Anything that has to do with Z, you throw away. And whatever you have left, I'm going to write on the board. Okay? So this is what you have left. Okay? That part, the first part, throwing away the zeta-related, Z-related components, that's pretty easy. So then we need to throw away a little bit more. Let's do that together. So first of all, on the right-hand side, I am writing 0 because there is no acceleration in this problem. So trivially, that dies away. So I have two equations, the two components of the two equations that come from the equilibrium statement. Okay, that equation in the box. Okay, so now we proceed with further simplification. Okay. Now, I have to essentially cancel a few components here, right? So I said I'm only interested in sigma theta theta. Well, sigma RR, it's going to be something that's negligible for us. We don't really care. So sigma RR would be the normal stress that is induced due to this force distribution, which is in the radial direction. So at this point, there is for sure a sigma RR. But at this point, right, on the plane with normal R in the direction R, sigma RR is 0 because it is a traction-free surface, right? On the inside, it's non-zero. But eventually, it's here 0. So the variation is it's going to be rapid from a non-zero to a 0 quantity. But I'm going to assume that sigma RR here is not for us a significant quantity. Okay, so to be exact, this is not 0 because there is a sigma RR. And for sure, it goes from a non-zero value to a 0 value along the radial direction. But our argument is that eventually, sigma RR is something that is negligible in magnitude. So I'm going to just not worry about that term so much at the beginning, and I'm completely going to omit it. So sigma RR is gone. Okay. Now, sigma R theta is just something that's not going to be there. In principle, it could be there. Sigma on the plane with normal R in the direction theta. It has to do with the traction distribution due to friction. Here it's non-zero. Here it's 0. For sure, this thing is non-zero, right? And there is a variation in the radial direction, but I'm going to omit because I'm going to eventually argue or hope that its magnitude is negligible. Okay? So what I'm left with, therefore, sigma R theta here is also likewise gone. I only see sigma theta theta, which I know depends on theta. I cannot omit that. And there is an FR and there's an F theta. So acceleration I've already omitted from the outset, but now I need to interpret what possibly FR and F theta are. So these are forces per unit volume that are exerted on the rope. One example I gave you before was, for instance, gravity, right? But it depends on the problem. So essentially, we're going to interpret this W and tau eventually as terms that contribute to FR and F theta as follows. So FR, it's force in the radial direction, right, per unit volume. So there is a force in the radial direction, but it is force per unit length, not volume. If I average this force over the cross-sectional area, I sort of distributed for analysis purposes on the cross-section. So it's W over A would have units of newtons per meter cube. So this is what I'm going to model as, for analysis purposes, as W over A. And now this has units that are suitable for the volumetric force. Okay, so then F theta, okay, so it is in the minus theta direction, first of all. I'm going to relate it to tau, so it's minus tau over area. But tau is mu times W, so it's equal to minus mu W over A, right? Or, in fact, this one I don't need to really model, if you like. If as soon as I have FR, I already see the relation here as well. W over A is FR. This is minus mu W FR. Okay. So if I directly write this, it looks strange. A component, tangential component of volumetric force where there is a friction coefficient. But when we think of it as being interpreted as the tangential, the friction force per unit length averaged over the cross section, then it makes sense. Okay? So now I have W over A. I have FR, which is interpreted like this. And I have F theta, which is interpreted like that, minus mu FR. Now at this stage, notice, however, I don't know what W is. Okay? If I know W, I know FR, or vice versa. If I know FR, I know W. But I don't know them. Okay? So that's something strange. So when you look at this equation, I have essentially two unknowns. I have sigma theta theta, and this is in terms of FR already, and I have FR. But I have suitably two equations for those two unknowns, so I should be able to solve them. So this is, in a sense, also it demonstrates something important about equilibrium. It does not only eventually deliver you what you are primarily interested in, which is the stress, but it delivers you more. Something that is critical to solving the problem. Its value will emerge from the solution procedure. Okay, so let's proceed. The first equation, that is pretty straightforward. Everything is almost zero. FR is equal to sigma theta theta over R. Okay, that's what we find. Okay, it's not a given. We find it from equilibrium. So we found FR needed for equilibrium. And then we can now go to the second equation. And the second equation tells us that del sigma theta theta del theta is equal to R times, this goes to the right-hand side, R times mu times FR. Or let's say mu times R times FR. But R times FR is sigma theta theta from 1. So it's mu sigma theta theta. Okay. And we're, in essence, done. Now I have an equation, derivative with respect to theta, in terms of the variable I'm interested in. So I can directly integrate that. So sigma theta theta must be a constant times exponential mu times the variable, the coordinate, which is theta. Okay. That's the solution of this differential equation. So what I can also do is now I can multiply left and right-hand sides by A. If I multiply the left-hand side with A, I get the tension on the rope. So this was the average stress. So now this is the tension. This is the, if you like, the real quantity I was interested in. And C times A I will define to be C prime e to the power mu theta. And now I can evaluate T at 2 points. For instance, I can evaluate T at an angle theta 2. And I can evaluate T at an angle theta 1, where theta 2 is greater than theta 1. And then if I take the ratio of the two, I will find T2 is equal to T1 e to the power mu delta theta. Okay, so this was the problem, right? So in principle, there are many terms. Eventually, we can think of the rope being constrained to just a plane of the cylinder, and it rotates as many times as we like. It doesn't matter, but just for analysis purposes, I took a section, a wedge from that rotation, T1 to T2 through a variation of delta theta, and there is friction. And now we find that due to the presence of the friction, the tension from one angle to the other angle through a simple rotation of delta theta, okay, is rising exponentially fast, right? So due to the presence of friction. So no friction, as we expect, nothing happens, right? The tension remains the same. But if there is friction, just after a few turns, we can expect that T1 can be very small, but T2, due to this term, can be extremely large. Okay? So that is the idea behind this type of, if you like, this type of structure. Okay. All right, so this is the, let me say, the power of equilibrium. Okay. Now, do you have questions, first of all? Okay, so I directly taken the equilibrium equation, I put it in cylindrical coordinate system. I had to make a few observations. But as soon as I make those observations, and such observations we always will have to make, so this is it's a small problem. It's certainly solved much faster than the problems that we will encounter in the upcoming weeks. But it has most of the features that eventually we will be interested in. Okay? The process will always be quite similar. A few observations, we end up with a differential equation, we have to solve it, etc. Okay? But there is one crucial feature missing in this type of an analysis, and it has to do with deformation. For instance, for sure due to this stress, the tangential stress on the rope, it's tangential or it's normal stress on the rope, on the cross section, the rope will change its length, right? Because it's a normal stress, sigma theta theta. And if you're interested in the total change in the rope from, let's say, that point, you turn around a few times, so the initial length was L, what's the new length? I have no knowledge about that, right? What I only have is the tension in the rope. So obviously, to think about elongation, I need to look at a few more things. And usually, in order to solve more complicated problems, we do have to consider deformation, not only stresses. Looking at stresses will not be enough. Okay? And so let us, therefore, take now one more step and think about how to incorporate deformations into such an analysis. And I'm going to call this material. It's also called constitutive modeling. Okay. And this is the last subtopic of this chapter. So we're going to try to model how the material responds to stresses. That's the meaning of material modeling. Okay? So put your pens, pencils down for a second, and let's have a look at this diagram that I will try to draw again and again, because it reminds us always of where we are and what we're trying to do. So we have a number of quantities presently, and the central quantity eventually, if we are looking at the complete solution of a problem, and the simplest quantity we have is displacement. Things deform under stresses and forces, and points eventually will get displaced. That's U. Okay. So now, on the other hand, we also have, of course, because there is displacement, there is a strain. Now, there are two ways to relate these two quantities. First of all, I can go, if I am given what the displacements are, I can easily calculate what the strain is. Okay? Strain is equal to 1/2 gradient U plus gradient of U transpose. So given the displacements, through this equation, I can calculate the components of the strain. Or I might be given the components of the strain, and I can try to find the components of the displacements. Okay? And I do that using compatibility equations. Right? So compatibility does two things. One, it lets me check whether there exists a strain, whether there exists a displacement such that strain has that form. And two, eventually it will help us, the components of the strain will help us integrate towards the displacement. So I'm going to write compatibility. And of course, at some point after compatibility, you have to do some integration. Now notice here there are 6 equations for every component. It's a symmetric matrix, right? It has 6 independent components. So for every component, there is a corresponding expression on the right-hand side. So 6 terms on the left, 6 terms on the right, 6 equations. And remember, there are also 6 compatibility equations. Okay? So 6 up here, 6 up down there. With integration, you can go that way, or you can go easier this way if you're given U. So these are 2 terms, but these are not the only things we have. So first we talked about displacement, then we talked about strain, and now we're talking about stress. And now there is also an equation where we see stress and displacement at the same time together, right? And that equation is equilibrium. Okay. And that's another equation, right? So now I see all the quantities that I'm interested in, and I have equations that link these quantities to one another, right? So let us box this thing, okay? Because, as I said, I'm going to repeat this diagram for you again to remind us how we attack problems. Now, let's now also count the number of unknowns and equations that we have here. So first of all, I count the number of unknowns. It's symmetric 6, right? 6 unknowns in stress. 3 components in displacement, that's 9. 6 components of the strain, so 15. So I have 15 unknowns. Okay? And now I count the number of equations that I have. 3 equations, right? This left-hand side is a vector, right-hand side is a vector. So 3 equations. 6 there, so 9 equations. Obviously, I don't have enough equations for these unknowns. I am short of 6 equations. So I need 6 more equations. And these equations eventually will come by relating stress to strain. All of these quantities are already linked to one another. The equation eventually that I'm missing and that I will now remind you is the equation that says, for instance, stress is equal to lambda epsilon v identity plus 2 mu epsilon. Okay, where lambda and mu are material constants, epsilon v is the volumetric strain. I'm going to remind you all of this. And there you go, you have 6 equations, right? 6 terms on the left, 6 terms on the right, the independent components. And now you have your plus 6 equations that you were missing. Okay? And this is called material modeling in particular. So material modeling, it relates stress to strain. That's what it does. And this one I have here is your good old linear elasticity. Not only linearly elastic, but also isotropic. Okay? So now let's recall that. But the idea is no matter what I do, these are in general not enough to have a complete solution. I have to have some material model that links stress to strain. That's the idea. Okay, so now let's recall linear elasticity. In fact, isotropic linear elasticity. That's what we're going to use exclusively in this course. Okay, so let us recall, therefore, our undergraduate expression. Okay, we've done this in 232. I'm updating the notation just to make a note for you. And I will tell you what those updates are, just to make sure that our notation is compatible with the widely employed notation in this type of a course. Okay, so let me go ahead while you're writing. Just remind you of the equations that we used to employ. Okay, so we had what we call the generalized Hookes law, which is nothing but the equations for isotropic linear elasticity. We generalized it in our undergraduate course, even towards anisotropy. But these are what we have for isotropic setting. So for any component of the normal strain, recall that the way to remember the equations is always as follows. So it's 1 over Young's modulus times the corresponding stress. But that's not enough. There is the Poisson effect. So we must always have minus nu sigma 22 plus sigma 33, the remaining two stresses, right? Epsilon 22, 1 over E sigma 22, right? They match. Minus nu, the remaining two normal stresses for every normal component. And then for the shear components, this is what we have. For shear components, they are always related to only their corresponding stress or strain. And 1 over 2 mu. Mu will be our shear modulus. Slight change of notation. That mu we used to call G before. So mu is a more common notation. And so this is the equation that we used to write in 231. Now instead of YZ, I'm writing 2,3, right? And instead of tau, I'm writing directly sigma 2,3. And instead of gamma, we are using 2 epsilon. Okay, so we have 2 epsilon 2,3 equals 1 over mu sigma 2,3. And dividing through 2, I obtain the equation that I have at the top for shear component. Right? It's just a change of notation. But this is the way that we're going to employ the equations. And this, of course, you've learned before, and that's something you have to remember. Now, what I'd like to do is I'd like to take those equations and express them in a slightly different way. In fact, I'd like to work towards this equation and introduce a new constant, lambda, as well. Okay? So before doing that, let me remind you a few other constants. So far we have the Young's modulus, the Poisson ratio, and the shear modulus, which for isotropy takes that particular form. So it's not an independent constant. It's related to E and nu. Okay. So we did have other constants. You will remember, for instance, the bulk modulus, right? So let's remember the bulk modulus as well. So B is equal to the bulk modulus 3,1 minus 2 nu. That's our bulk modulus. And the meaning of the bulk modulus eventually came through the following small exercise that I can remind you again. So essentially what we had done is we went to the normal components of the strain. And all I did was I summed both left and right-hand side. So I sum the left-hand side, and I have a quantity which we defined as epsilon v, the volumetric strain. So that's epsilon 1,1 plus epsilon 2,2 plus epsilon 3,3. Now, that's the left-hand side. And when I sum the right-hand side, I have only 1,1, 2,2, and 3,3. And everything will be in terms of that sum. So we also define something called sigma h, the hydrostatic stress, which is sigma 1,1 plus 2,2 plus 3,3 divided through 3. Okay? So when you sum the left and the right-hand side, you find eventually that epsilon v is directly related to sigma h through a constant b, which is the bulk modulus. Okay? So this was the equation that we had derived. And that gives the meaning to the bulk modulus. Now, I'd like to define a new constant that you had not seen before. And that constant is called lambda. Let's call it the Lamé constant or Lamé parameter. Lamé, L-A-M-E. And it is defined as 3b Poisson ratio 1 plus Poisson ratio. That's the definition. All of these constants are eventually defined because it simplifies our view of a relation, right? So we define B and not directly write this, because once we define B, then we have a neat expression. Instead of retaining these so many terms in that relation, I have a B. Likewise, I'm defining lambda so that eventually I have an expression in that case, in this case, the red equation, which looks neat. There's only one constant, and it's defined in terms of things that we already know from before. Okay, so now let's keep those in mind and move on to a compact expression that relates stress to strain. So let's say for a compact representation, let's define the identity. Okay, so its components will be a matrix, and it's a diagonal matrix with only ones on the diagonal. Okay, and now let's also do the following. Let's indicate the components by not ij, but let's pick a particular notation, delta ij. Okay. So normally if I had a matrix A, I would call its components aij. Now I have a matrix I. I'm calling it delta ij because this is sort of a common notation. And delta ij, it's called the Kronecker delta. And Kronecker delta is defined as follows. It is equal to 1 if the two indices are the same and 0 otherwise. Right? Which defines the components of the identity. If I'm on the diagonal, it's 1. Otherwise, everything else is 0. And now, having defined that, let's make essentially some observations. And I'd like to actually continue down here, but I remember I need to make use of the board down there. So, okay. So I'd like to make use of these equations here. So first, let us look at shear. Okay. Shear is when I is not equal to j, 2, 3, 3, 1, 1, 2. And it doesn't matter whether it's 2, 3, 3, 1, or 1, 2. What matters is I is not equal to j. And in that case, what I observe that epsilon ij is equal to 1 over 2 mu sigma ij. So for any choice of I not equal to j, that relation is true. Okay? Now I will take a step further and use the fact that mu is equal to E over 2, 1 plus nu. I'm going to go ahead and plug that in there. So E over 2, 1 plus nu. So it's going to be 1 plus nu over E sigma ij. Okay, that's the way I like to eventually make use of it. That is for the shear components. And now we have the normal components. Now what's special about normal is that I is equal to j. And now I'd like to write epsilon ij. Now the beginning part is easy. So epsilon ij for I is equal to j. So it's 1, 2, or 3 is sigma ij, I equals j, divided by E. So 1 over E sigma ij. Now, this part looks a tiny bit tricky, but let me do a trick here. I'm going to add sigma 1, 1, for instance, to the first one, and subtract sigma 1, 1. Okay? Likewise, here I can add sigma 2, 2, and then subtract sigma 2, 2, etc. Eventually, in all of the cases, something identical happens. 1, 1 plus 2, 2 plus 3, 3 is 3 times the hydrostatic stress by definition. And now 3 hydrostatic stress minus the component I'm interested in. So in every case, I can write the remaining part as minus nu over E 3 times sigma h minus sigma ij. This is my small trick for explicitly inserting sigma ij in there. Okay. All right. So we are in good shape. So I'm going to take that right first. So minus 3 nu over E sigma h. And then 1 minus nu minus, so 1 plus nu. 1 plus nu over E sigma ij. Okay, so now one further trick. So I is already equal to j, right? Because I'm looking at the normal component. Which means that if here I insert a delta ij, in the present case it is already, I is equal to j, so it's already 1. Nothing changes, right? It's still the same equation. But now if I have this and now I write or assert that in general epsilon ij is equal to minus 3 nu over E sigma h delta ij plus 1 plus nu over E sigma ij. If I write that, that is now true whether I is equal to j or not. Okay? Because if I is equal to j, this drops out. So in fact, whether it drops, it is automatically equal to 1, sorry. So it's equal to that term. If I is not equal to j, this is 0. It dies, and epsilon ij is equal to that term. So now I have an expression that is correct whether or not I is equal to j. Okay? So that's a nice small step. In fact, why don't I do the following? Since this equation is already present there, why don't I now write this in a general notation? So that's the matrix. Instead of delta ij, I can write the identity matrix. And instead of sigma ij, I can write sigma. Okay? So this is our first general equation. So this equation is pretty much nothing else than our standard equation. On the left-hand side, strain. On the right-hand side, stress. It's just a little bit rearranged and put in a slightly more fancier form. It's just one equation instead of 6. Okay? Well, visually one equation, but of course there are 6 components there. All right, and now I am almost done. What now I aim to do is have stress on the left and strain on the right. So let's rearrange that. Okay. So I'm going to take this term, put it to the left-hand side, step number 1. So sigma is now left by itself. And then I have to multiply both sides by E over 1 plus nu. That's what I do. Okay, so stress is equal to 3 nu over 1 plus nu, right? I multiply with E over 1 plus nu, sigma h, identity, plus E over 1 plus nu, epsilon. Now, in this equation, I wanted to have only E and nu because that's the natural thing to do. But now that I'm switching back to a different arrangement, I remember once again where this came from. This came from the fact that this term is actually equal to exactly 2 mu. I originally had mu. I switched it back. And now I also remember that sigma h, the hydrostatic stress, can be written as the bulk modulus times the volumetric strain. Okay? So now I'm making use of everything that I had before. And finally, I remember the new constant which I introduced, which is 3b nu over 1 plus nu, which was the Lamé constant, lambda. And therefore, I have a nice expression that says sigma is equal to lambda epsilon v identity plus 2 mu epsilon. Okay? And this boxed expression, I expect you to remember. Okay? So it's not too hard. You will use it a number of times again and again, so eventually it will sink in. You should memorize it because it will remind you how to relate stress to strain. We can also write it in components. Okay. This, of course, is valid in any coordinate system. Epsilon v is always some of the diagonal components. But let me write it in components as well, explicitly. So sigma ij is epsilon v delta ij plus 2 mu epsilon ij. As usual, whenever I solve a problem or I make a derivation in class, please go over it. Make sure that you understand the steps. It will be useful, some parts of it, in the future again. Any questions? Okay, so we're done with stress and equilibrium. So next time we meet, we will start solving some problems. All right, so that's all for today.